Okay, so we're going to go over lesson 8, which is exploring the symmetry and graphs of quadratic functions. And so let's go over the standards for this lesson. Wrong one. Perfect. So there's a few standards we got to cover. So first off, A1F IFB3 for a function that models a relationship between two quantities, interpret key features of graphs and tables in terms of quantities, and sketch graphs showing key features given a verbal description of the relationship. So that's one thing we want to do. The next thing we want to do is A1F IFB5, which is calculate and interpret the rate of change of a function presented symbolically or as a table over a specified interval, estimate the rate of change from a graph. So that's another thing we want to do. We want to be able to graph linear and quadratic functions and show intercepts, maxima, and minima. That's important for this one, which is a subsection of A1F IFC6, which is graph functions expressed symbolically and show key features of the graph by hand and using technology. So let's get right into it. So let's go over some vocabulary. Given a quadratic in standard form, so you should be familiar with this by now, ax squared plus bx plus c, the vertical line given by the equation of the graph x equals negative b over 2a is called the axis of symmetry of the graph of the quadratic function. The point where the graph of a quadratic function and its axis of symmetry intersect is called the vertex. So it's the turning point of your parabola. So it's this part of the parabola. And then in behavior of a graph, if I have a quadratic in the form of ax squared plus bx plus c, or if it's in shifted form, so a times x minus h squared plus k, vertex form that is, the quadratic function is said to open up if a is greater than 0, so it's going to open up if a is greater than 0, and then open down if a is less than 0. So if a is greater than 0, then f has a minimum at the x-coordinate of the vertex, f is decreasing for x values less than or to the left of the vertex, and f is increasing for x values greater than or to the right of the vertex. So what's that's saying is if the graph is concave up, then if I go to x values less than the axis of symmetry, then I will be decreasing on this interval. Okay, so my function is decreasing. So if you imagine me riding a bike on this curve, I would be going downhill. And then to the right of this vertex, right, I would be increasing. So I'd start to increase up the hill. But if the opposite is true, if the graph would be concave down, so if you imagine if this graph was flipped or reflected, then f has a maximum at the x-coordinate of the vertex, and f is increasing for x values to the left of the vertex, so I'd be going uphill, and then for x values greater than or to the right of the vertex, I'd be going downhill, okay? So here are some examples of curves found in architecture of the world, and some of these are represented by, some of these, they kind of look like quadratics, but it's important to say that they're not, okay? So they cannot actually be modeled with quadratic functions, but are catenary curves, but they're quadratic-like and can be used for our exploration purposes. So I want to make sure that you guys know that. So these are not exactly parabolas, but they're great demonstrations of what a parabola would look like. So if you take a look at these structures, there's some 2 questions down here for us. It says, how would you describe the overall shape of a graph of a quadratic function? Well, it either bends up or bends down, has a maximum or a minimum, okay? So it has that like bendy nature. So they're unlike lines, but they're a very important structure and equation for us to look over whenever we're studying mathematics. And it says, what is similar or different about the overall shape of the above curves? Well, if you take a look here, they each have a peak. So they open down. So if we were to model these with quadratics, our quadratics would open down. But if you take a look, some of them are wider. So if you take a look at this one, it's a little bit wider than this one, or these are a little bit thinner, and they kind of bevel down pretty quickly. But they all have maximums, and they all are concave down. So here's our first exploratory challenge. So I'm going to draw this graph in red. And so let me draw this guy. switch over to my, yeah. And so, right, I've got 1, 2, 3, 4, 5, 6, 7, and then 8, and then -1, -2, and then 1, 2, 3, 4, 5, 6, and then -1 down here. So if you take a look here, this is my graph, and so they're asking me to fill this chart out. So I will write down the chart. And then we've got, it's there, it's up at +8, it's right there, right here, right here, right there, right there. And so what they're asking us to do is to graph this function, or not graph it, but take a look at it and then fill out this table over here. So we're going to do that. So if I go over here, I've got -1,8 as a point, so that's given to me. And then the next thing that I'm going to do, you can actually pick any point on this, but we're going to go by the standard that they gave us. So if I increase x by 1 in each one of these, in this table, then you're going to get a nice pattern and you're going to see some symmetry here. So if you take a look here, I've got, if I plug in 0, I get back 3. If I plug in 1, I get back 0. If I plug in 2, I get back -1. I get back, if I plug in 3, I get back 0. If I plug in 4, I get 3, so that's the point that they gave me. And they also gave me 2, -1, so that's down there. But the other ones I'm supposed to eyeball, so if I plug in 5, I get back 8. And so already you should be kind of seeing this symmetrical nature. You take a look here, I've got 2 points here that their outputs correspond. And then if I've got these two, their outputs correspond. And then these two, their outputs correspond. And if you take a look, all these x values are the same distance away in pairs. All these x values that have pairs of outputs that match are the same distance away from your axis of symmetry, which is this guy, right? It's that distance there, okay? And so we're going to do this again for graph B, which looks kind of like this. So you have this graph here, and I'll go ahead and draw it for us to reference. And again, I'll draw that table. That's right, I've got x here, f of x, and then let's see. 1, 2, 3, 4, 5, 6, 7. Okay, so take a look here. This is the lesson, and then over here I've actually got the graph outline, so we kind of want to fill this out. So if you take a look here, right, if I plug in these x values, right, the precedence that they've kind of set here is that -3 goes up by 1, so the next one would be -1 naturally, 0, and then 1. And then if I go to the left, right, if I go down, it's going to be -4, and then -5. And so I'm trying to find what these outputs would be. So over here, -5 is, its output is also -5. So I'm going to write that down. And then if I plug in -4, its output is 0. And then 3 and 4 they've already given me. So if I look at -1, it has this nice symmetrical nature, so my output would be 3. And then 0, if I plug that in, right, it's hitting the x-axis there, so that would be 0. Its output is 0. And again, we have this nice symmetrical nature. Right, these two guys match. Their outputs match at least. These two match. Their outputs match. And then these two match. And the reason is because this quadratic has an axis of symmetry where if I go in certain directions, I'm going to have the same output, right? If I go to the one right of this axis of symmetry, my output is going to be 3. So -1, 3 is my output. And then if I go to the left one, I'm going to have the same output. So it has this nice reflective property over this axis of symmetry. So that's something to kind of note. So then we'll go over here to the lesson, and we'll continue answering some of these questions. So the first thing it wants to know is for graph A and B, it wants to know the x-intercept. So we're going to do these. So if I go up here and I look at graph A, right, it wants to know the x-intercepts. Well, that's where the graph hits the x-axis. So if I take a look at my graph, it hits the x-axis right here and right here. And so if I take a look at the table, it's actually where my output is 0. So it's this guy and this guy. So I write those as coordinates. My x-intercepts are 1, 0 and 3, 0. So you might be familiar with lines. Lines have one x-intercept, but quadratics can have a maximum of 2. Okay, so if this quadratic swoops and hits the x-axis twice, then you have 2 x-intercepts. If it hits it once, you have 1 x-intercept, and then you can have a case where the quadratic in the real xy plane has no x-intercepts. Okay, so that's the x-intercepts for graph A. So if I take a look at graph B, I can do the same thing. Its outputs are 0 when you plug in -4 and when you plug in +0. And so we can look at the graph of it, and we can also see, right, it hits there and right there. So those are the x-intercepts. And they are coordinates. So when you're listing the x-intercepts, just don't just say it's -4 or +0, not +0, -4 or 0. It's going to be -4, 0. So it comes as a pair, and then 0, 0. And that is it there for that one. So let's see what the lesson says next. Okay, the next thing they want to know is the vertex. Well, the vertex is the turning point. So let's see, I'm going to pick a different color here. Do it in pink. The vertex of graph B is actually the highest point. So it's up here. So that would be negative 2, 4. Okay? So negative 2, 4 is my vertex. And so whenever I write the vertex, it's also a coordinate pair. And notice that this is, okay, we'll get to that in here in a second, never mind. And then up here, it's the lowest point on the parabola, so that's 2, negative 1. So my vertex here is 2, negative 1. Okay? And that's all I have to say about that. So the next thing we'll look at is the lesson. And the next thing they want to know is the sign of the leading coefficient. So if I saw the formula, or not the formula, but the equation of both of these functions, what would the sign of the leading coefficient be? And that's specifically the a term in a standard quadratic. So we'll say sign of leading coefficient. Well, the sign of the leading coefficient in this case, since it's concave up, it's going to be positive. So a is greater than 0 here. And then down here, I want to know the sign of the leading coefficient. Well, this quadratic opens down. So his sign of the leading coefficient here in the second graph I know a is negative. Has to be negative in order to open down. Okay? And that's it. That's all I'm going to do for that part of the lesson. So if I go back over here, does the vertex represent a minimum or a maximum? Okay, well, I can take a look at graph A, and I can take a look at this, and if you think about it, right, if this is a quadratic, and if I'm riding a bike on that curve, right here I'm going downhill, so I'll point to that, so I'm going downhill, 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 and then uphill. So if I think about this, it's kind of like the bottom of a hill, so this is a minimum, okay? So 2, negative 1, its vertex is a minimum. And then if I look at graph B, negative 2, 4, that graph is a maximum. So it swoops up and goes back down. So if I was riding a bike on that, I'd be going uphill to the left and then downhill to the right. So increasing and then decreasing, so that's going to be a maximum. And then the next thing they want to know is they want to kind of talk about points of symmetry. So f of negative 1 and f of 5, okay? So let's take a look at that graph and find f of negative 1 and f of 5. So for graph A, f of negative 1, if I plug in negative 1, I get back 8. And then if I plug in 5, I get back 8. So somewhere over here, I'll write for graph A, f of negative 1 equals f of 5, which equals 8. So they both have the same output, okay? So, sorry, you can see that now. They both have the same output. And it says, is f of 7 greater than or less than 8? And explain. So if I go back here, if I take a look here, 7 is not on the page, but if you take a look at the graph, it's actually going up. So it has this nature where it's like pointing up. So if I plugged in 7, since this is increasing, I know that whatever f of 7 is, it's got to be greater than 8. So right, f of 7 is greater than 8. So if f of 7 is greater than 8, what that's telling me is that this function is increasing. And so f of 7 is greater than 8 because f of x in graph A is increasing. Okay? And that is it. That is it for that one. So let's take a look at what the lesson is asking for graph B. It says find f of -1 and f of -3. Well, if I plug in -1, I get back 3. If I plug in -3, I get back 3. So over here I can say that f of -1 is equal to f of -3, which is equal to 3. And this is also by symmetry. So if you take a look at our axis of symmetry, it's x equals -2. And so it's right halfway in between -1 and -3. So if you take a look, right, f of -1 is actually 1 less than, 1 greater than -2, and then -3 is actually 1 less than -2. So they're the same distance away, just in opposite directions. So I'm going to show you that here in red. So right here, this distance is the same as this distance. So anytime you have that, you're going to have the same output in quadratics. It has that symmetrical nature. It's pink. I need to do it in red, sorry. Maybe you can see that a little better. And so the next thing it asks us, it says f of 2 is equal to -12. Predict the value for f of -6 and explain your answer. Well, that's that symmetry thing. So f of 2 is equal to 12, -12. So it tells us, okay, f of 2 is equal to -12. Well, if I plot that here, so -6, -7, -8, -9, -10, -11, and then -12. So f of 2 is equal to -12. Well, if you take a look here, how far is 2 from -2? And so if I try and find this distance and I count from -2 to +2, the distance is 4. Okay, so it's 4 units positive to the right of it. So if I want to know what f of -6 is, well, if I think about it, if I take and measure from, right, take a look at here at -6, if I measure this distance, then that will also be 4 units away, just in the negative direction. So if symmetry works and this graph goes through -12 down here when I plug in 2, then it's also going to go through -12 whenever I plug in -6. So I can kind of extend this graph and you can see it, and there it is. And that's what I want to talk about with that one. So f of 2 equals -12. What is f of 6? Well, it's going to be the same value in this case, because -6, sorry. It's going to be the same value in this case because of symmetry. So I'm going to say that, by symmetry. This is true by symmetry. And then the next thing they want to, excuse me, next thing they want to talk about is increasing and decreasing intervals. So for graph A, it wants to know over what part of the domain is the function depicted by the graph increasing, and then what part is it decreasing. And then they ask kind of the same question for graph B. So we'll go back over there and we'll talk about that. So if I look at graph A, I want to know over what part of the domain is this graph decreasing and increasing. So if I look at decreasing, so I'm going to say this down here, no, I'm going to say it over here. So graph A is decreasing. Well, if you take a look here, if I'm riding a bike on this curve, I'm going downhill over this interval. So domain, remember, it has to do with the x values. So if I'm looking at these outputs, I'm looking on the negative side of the graph. So from -infinity, so all the way over here is -infinity. So I am decreasing from -infinity, and this is not a coordinate. Remember, this is an interval of a domain, so you're starting at -infinity, and then you're going to a certain point. So I am decreasing on this interval. If I'm riding a bike, I'm going downhill from -infinity all the way to positive 2. So that's the interval of decrease. And I can switch it, and I can think about the levels of increase. Well, at 2, I switch from going downhill to uphill on that bike. So I start to increase, and I go up and up and up and up on forever, and this graph seems to show that this behavior continues all the way to positive infinity on the x-axis. So any value that I plug in here, 7, 8, 9, 10, it's going to keep getting larger and larger y values. So that's increasing. So 2 to infinity. And so it's going to be a similar process with the second graph. It's just because of the concavity that it switches which side am I increasing on. So if you take a look here, toward negative infinity, if I read this graph from left to right, my bike would be going uphill. So this is an uphill climb all the way until I reach negative 2. So my function here over here on graph B is increasing. It's increasing from negative infinity to negative 2. I think that's right. Yeah. And then at negative 2, 4, that's my maximum. So I stop, my bike reaches the top of the hill here. If I'm reading this graph from left to right, I'm riding this bike uphill. And then up here, if I reach this peak, it starts going downhill. So from that point, the graph switches from increasing to decreasing. So negative 2 to infinity. So this is increasing, and this is decreasing. So it wants to know what part of the domain am I increasing and decreasing on. And then the last thing it wants to know is average rate of change. Okay, so we're going to need to know this over the interval, but these are x values that they're dealing with, and it's over this part of the domain. So we're going to take a look at graph A and kind of go over what average rate of change is. But first, we need a formula. Okay, so average rate of change is the slope between 2 points. Okay, so if I want to calculate the slope between 2 points, then I'm going to do y2 minus y1 over x2 minus x1. Okay, so, or another way of writing it is f of x2 minus f of x1 over x2 minus x1, where this interval that they handed me, x1 is in the first position, and then x2 is in the second position. So what I can do is I can go up to the graph and kind of use this, but I'm going to give you a second to kind of copy this down, and then pause the video by all means here to copy that down, and then we'll go over one part of graph A, and I'll do the next part of the next video and kind of upload this one. So so if I take a look at this lesson, it's telling me to find the average rate of change from negative 1 to 0. So my x1 would be negative 1, and my x2 would be 0. So I'm going to switch back here. So negative 1 to 0 is the interval. So I'm going to do this over here. Negative 1 to 0 is my interval. So that tells me x1 is equal to negative 1, and then x2 is equal to 0 for my formula. So then, what I have to do is look at the graph and find f of x1, the output for when I plug in negative 1, and then f of x2, the output for when I plug in 0, and then perform the calculation. So I want to show you kind of what I'm talking about over here. And rate of change is the slope between 2 points. So let me pick a color here. I'm going to do orange. No, I'm going to do green. You look Christmas. Or maybe not. This is a little pinker on that screen. So 0 and negative 1 are my outputs. So if I look at negative 1, it's all the way up here at 8. And then 0 is down here at 3. So my whole goal with this is to find the slope between those 2 points. So what I'm calculating is if I draw in that line, it would be the slope of that line. Okay, so this is called a secant line. So that green line is called a secant line. So this is just extra information, but it kind of has to do with upper level math, including calculus. So eventually you talk about a tangent line. So if you want to learn more about that, I would take calculus. But that is a secant line cutting through those 2 points. And we want to know the slope of that line. That's the average rate of change from -1 to 0. That's what the average rate of change is. So we have our inputs and our outputs. So they said they want to know the rate of change from -1 to 0. I'd take a look at the outputs over here. So let me do light blue. So my output for -1 is 8. So you can kind of see that from the graph. If I plug in -1, you get back 8. And then if I plug in 0, I get back 3. So if I plug in 0 here, I get back 3. So that's the other thing that I want to look at for the rate of change. So if I go over here, -1, if I plug in -1, I get back 8. If I plug in 0, I get back 3. And if you take a look here, this slope is downhill for this line. So I should get a negative value for my average rate of change, right? In fact, we can kind of ballpark this and probably even get it exactly. If you take a look at the slope of this line, this is down 1, 2, right? Down 5, so -5, and then right 1 over 1. So the slope is -5 over 1, so you can kind of eyeball that. So the average rate of change from -1 to 0 on this interval is -5 over 1. And something that's going to be a little different with these is that whenever we deal with quadratics, their average rate of change between 2 points changes over time. It doesn't stay constant. You know, I could pick 2 points and it be similar, and I can pick 2 points and it be completely different. It's not true for a line. Whenever we graph a line in y equals mx plus b form and we find its slope, that slope stays constant. Okay? Not the case here for quadratics. So I should get -5 over 1, but we're going to go ahead and calculate this. So remember our formula, and then we're going to plug in the values. Our formula for average rate of change, which you'll also see it as delta y over delta x. It just means change in y over change in x is going to be 3. So f of x2, so let me write that out before I do that. F of x2 minus f of x1 over x2 minus x1. So it's going to be 3 minus 8 over 0, which is x2, minus -1. So notice that since this is a negative, I have to carry that sign even though there's a subtraction sign between. So if I calculate this out, I get 3 minus 8, which is -5. And then 0 minus a -1 is going to be +1. And that's all I'm going to do for today. I'm going to go ahead and upload this. But I hope this helps out, and we will continue to go over the rest of this stuff soon. And that is it for today. So take it easy.